Hey everyone, this is Joshua Sturgell. In this video we'll be talking about spectroscopy, and again we're going to be working through a specific compound and the data for that compound and be able to discuss some of the characteristics of it. So I'm going to go ahead and scroll down here. Here is the H-NMR, the C-NMR, and the IR data for a compound with a molecular formula of 7 carbons, 9 hydrogens, a nitrogen, and an oxygen. So I'd encourage you to pause the video at this point and see if you can work through the data and use the formula to deduce a reasonable structure for this compound. Alright, I hope you had an opportunity to work through that. I'm going to go ahead and drag over the answer. So the name of this compound is 1-amino 2-methoxybenzene, and there's the structure provided. So the first thing I want to start off with in this problem is the IHD, or the index of hydrogen deficiency. So let's run through that real quick. What the index of hydrogen deficiency tells us is the amount of double bonds and or rings we have in our structure, which is very useful, and this is a very useful formula to memorize. It's 1/2 times the number of carbons, 2 times the number of carbons plus 2 plus the number of nitrogens in our compound, and we subtract from that the number of hydrogens plus the number of halogens in our compound, and it's 1/2 multiplied by all that within the parentheses. So if we plug in the numbers that were provided based on our molecular formula, we have 2 times 7 plus 2 plus 1 with our single nitrogen, and then we subtract from that our 9 hydrogens. I'll go ahead and write that we have 0 halogens. The answer to the math there will be 4, and that is very useful. We know that we have 4 double bonds and or rings within our compound. That's very useful when you're starting off with a spectroscopy problem. And those 4, and for our particular compound, we have 3 double bonds and a ring, which is the 4 that we got from our index of hydrogen deficiency. Those 3 double bonds in the ring is the benzene ring that we see. Moving on to the H-NMR, let's go ahead and identify all of our hydrogens in this case. We have 3 methyl hydrogens over here that I'm going to go ahead and label as H1. We have a hydrogen here, 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 and here on the benzene ring, and then these hydrogens up here with the nitrogen I will label as H2. And let's just go H3, H3 across the board there on the benzene ring. In previous videos, I personally feel the H-NMR data was a little easier to read and work with. This H-NMR might be a little bit more tricky to see, but we have 2 peaks here provided, or 2 peak clusters here provided. The splitting is very messy, but we are provided some integration curves. This peak down here at about 3.9 corresponds to the methyl hydrogens as part of the methoxy group coming off of the benzene ring, H1 there. The peak cluster we see up there around 7. If we remember correctly, the hydrogens that correspond to an aromatic ring, those shift values tend to fall between the range of 6 and 8. Okay, which is exactly where this peak cluster is showing up at. So all of our H3s are shown up there, and it's a kind of a cluster, and it's kind of spread out in a way, and the integration curve is kind of curved in an odd fashion, because technically the hydrogens closer, those 4 hydrogens labeled H3, they're some are near a methoxy group, some are near an amino group, and the oxygen within the methoxy group and the nitrogen within the amino group will have different electron withdrawing capacities. So those hydrogens labeled H3, they do all have slightly different shift values, and that's why this cluster of peaks is a little odd, as well as the integration curve. In theory, the hydrogens closer to the methoxy group, closer to the oxygen, should be a little bit more de-shielded. So that leaves us with our hydrogens labeled H2 coming off of the nitrogen. We have two hydrogens there, and those are actually showing up here as well, around 3.9, with a very similar shift value to the hydrogens labeled H1. Again, this can be a little confusing. The hydrogens part of amino groups typically have shift values between 1 and 3, and they can vary pretty widely. These hydrogens are on the higher end of that. They go past 3 because they're coming directly off of a benzene ring, and benzene rings tend to be electron withdrawing groups as well. And another useful tool to confirm what we just did is we have 3 hydrogens that we labeled H1, and we have 2 hydrogens that we labeled H2, a total of 5 hydrogens showing up at this integration curve right here, and the 4 hydrogens that we identified within the benzene ring are showing up at this integration curve here. The integration curve is taller on the right side. The integration curve is shorter on the left side, meaning there are more hydrogens corresponding to that integration curve in a 4:5 ratio as far as the integration goes. So that's a useful way of confirming the information that we're working with here. Moving on to the C-NMR, we have 1, 2, 3, 4, 5, 6, 7 peaks showing up here. This is a solvent peak that I'm going to go ahead and white out real quick, just so we don't get confused. With the carbons over here on the compound, I'm just going to go ahead and label this one as carbon number 1, carbon number 2 there. Let's just go 3, 4, 5, 6, and 7 there. Our carbons labeled 4, 5, 6, and 7. Those are all they're all part of the benzene ring, and they have no other directly attached electron withdrawing group next to them, and so they're going to be on the lower end of our shift value range of 100 to 150. Carbon number 7, closer to the oxygen, which is very electron withdrawing, will be the highest of those 4 peaks. So this peak right here is carbon number 7. And then I'd go carbon number 3, as he is directly adjacent to a nitrogen, which is electron withdrawing. And then carbon number 6 being closer to the oxygen. And carbon number, I'm sorry, I meant to say carbon number 4 being closer to the nitrogen. And not directly attached, just like carbon number 7 was not directly attached to the oxygen, but close to the oxygen. And then I'd go carbon number 6 and carbon number 5. Carbon number 7 and 6 are closer to the oxygen, and they're higher and relatively in shift values than carbon number 4 and carbon number 5. The 2 highest peaks on our C-NMR will correspond to carbons number 2 and carbons number 3. Carbon number 2 will be more downfilled than carbon number 3 because carbon number 2 is directly attached to an oxygen within the benzene ring. And so it'll be on the higher end of that 100 to 150 shift value range. And same goes for the carbon attached to the nitrogen within the benzene ring. He too is attached to an electron withdrawing atom, and he'll be more downfield with a higher shift value. That leaves us with carbon number 1 over there as part of a methyl group. It's part of the methoxy group coming off of the benzene ring. If you recall, the shift values for methyl carbons typically is in the 0 to 35 range, and can jump up to near 50. This is higher than that range that we're used to seeing, and the reason for that is because that carbon is directly attached to an oxygen, which is directly attached to a benzene ring, and so there are a lot of electron withdrawing a lot of electron withdrawing groups in that direction, making that carbon particularly deshielded. Let's jump to the IR real quick. For the most part, everything that we see below 1500 is a little, or is very messy. It's hard to determine any super strong evidence as far as confirming this compound with the data we've been working with. Something that we do have though is we have a nitrogen and an amine bond, a nitrogen between hydrogens bond showing up down here in the range of about 3,350 to 3,500. This right here. That's shown up, and we obviously have that bond right there in our compound that I just pointed to in green. We as well have our both sp2 and sp3 carbon-hydrogen bonds. The sp3 carbon-hydrogen bonds show up typically a little bit under 3,000. The sp2s show up above 3,000, and so we see a cluster of peaks, cluster of wavelengths there with around that area. So that's good data there. And then the last worthwhile thing to point out may be the fact that we have a benzene ring down here. In particular, we have an orthobenzene ring, which shows up around 750. And this peak right here does seem to be showing up right about there. Again, the evidence for that isn't super strong, but it's there. Something that we would look for also might be the carbon single bonded to an oxygen bond there or there, and that bond usually shows up in the range of about 1,000 to 1,200. And I guess we could say that bond is right there, the C double bond, or the C single bonded to an oxygen. But again, it's a little messy and hard to say that for sure. But there's the data. Hopefully that helped working through the H-NMR, the C-NMR, and the IR for 1-amino 2-methoxybenzene.